In this video we're going to talk about correcting stress-strain curves to account for a preload that is often seen when using electromechanical testing machines. We'll talk about why this is important to do this correction, and in the process we'll show you some tips on using Excel to come up with a stress-strain curve. Okay, so first of all, if you're using an electromechanical test frame that's opposed to a servohydraulic test frame, and you're using mechanical wedge grips. Okay, so let's make a note of that. You put your testing specimen into the grips and you tighten the grips up. And as you tighten them, the tightening of the wedge grips induces a preload on the specimen. Now this preload may seem insignificant, maybe just a couple £100, but depending on the strength of your specimen and the dimensions of your cross section, that could actually result in quite a bit of stress. Okay, so after this preload is done, and you need a preload in order for the grips to get an initial bite into the specimen and to keep loading. After the preload is done, you do not want to zero away that load. That preload actually induces some strain in the material. Now at this point we don't have our extensometer on our specimen yet, so we have no idea what that strain is. But if we know in the end that we have a linear elastic material, at least in the initial portion of the stress-strain curve, we can account for that preload and the strain value on that preload. So let's make a note. Here the extensometer does not measure this initial strain. So what our stress-strain curve ends up looking like is it starts off at some stress here, and if it's linear elastic it takes some certain slope and then it comes over here. Now even though this point has stress on it, but the extensometer has not measured any strain, so it starts off here at this zero strain point. But really, if we were to extend this as a straight line until it hits the horizontal axis, there's a certain amount of offset strain. And what we need to do is we need to calculate that offset and then add it back into all of our strain values so that it starts at 0 and then it picks up and continues our stress-strain curve as it does with the rest of our data that we collected. So this is important, and I'm going to go through an example and I'll show you that the amount of strain and the stress that's initially induced from this preload shouldn't be ignored. It's important to never remove the load by zeroing the load cell when we induce a preload in the specimen. Your stress-strain curves will be off. You may have the correct slope for your modulus of elasticity. You might have the correct ultimate stress, but a lot of your other values will be incorrect. Alright, so let me show you how to load in some data into Excel, and then we'll take it from there. Okay, so I have some data that's preloaded into Excel, but let me show you how to import data. If you have a tab delimited data file, it's pretty straightforward. You go in here and you select your data file. If it's a text file, make sure you select all files and then open this, and see it says delimited. That's the thing in between the data points. Hit next, and in my case I have a tab delimited file. You can go in here and you can double check to see if your data is getting in the right columns by looking to see where these lines are at. There are other options, commas, semicolons, spaces, and such, but you can import the data now by hitting next and then finish. So your data may look a little bit different, but this is what mine looks like for this one that I just imported. Here's the extension, the time, the load, extensometer, and adjusted strain from the testing machine. These mean different things for different testing machines, so you have to be a little bit careful. Let's go back to my original data set. I used a 1-inch gauge length extensometer, and this number right here is the extension of the extensometer. Since it's a 1-inch gauge length, and I know that strain is the change in length divided by the initial length, that initial length is 1 inch. This is effectively the strain in the material. Well, let me put it this way. It's the strain measured by the extensometer on the material. Here are my thickness and width. I had a rectangular cross-section bar in inches. And let's also take a look at this value. Now, even though I zeroed my extensometer electrically by pressing the 0 button when I had that on the testing machine, I didn't quite start off with 0 strain when it started taking data. This should probably be accounted for. It looks like it's about 34 microstrain. So what we're going to do is we're going to subtract that number from all of our values. So let's make a column here, and I'll call this strain. And I'm just going to have an offset. I'm going to copy this value. I'm going to paste it over here. Okay, and now I'm going to take this column and I'm going to take that data point, and then I'm going to subtract off this one. Now, if I don't want that the I2 to change, I'm going to put a $sign in front of these values right here, and that way it's always using that particular cell I2 even when I copy this down. Okay, so now I get 0. I'll take it, I'm going to copy that, and I'm going to drop this down so I can find the end of my data. Now to quickly get down to the end, I'm going to hit the end button on my keyboard and then the down arrow. That will get me down there. So I'm going to go here and down to the bottom, and at the same time I'm hitting shift. As I click on this, I'm going to go up to the top part of this, and then I'm going to paste this in. So now I have these cells, every single one of them has this offset from here to here. Now I could put in my gauge length. It's 1 inch, so I'm not going to worry about it. If I used a different gauge length extensometer, then I would want to make that accommodation in here. I'm not going to worry about the time column. I can convert that to seconds if I want. But now let's take our load and let's convert that into stress. Okay. By the same way, I'm going to hit my plus sign to start a formula. I can go over here to the load. 129 pounds. That doesn't seem like very much load. You might be tempted just to ignore that, but we will show why you cannot just ignore that. Now we're going to go over here. We're going to divide by the cross-sectional area, which is this number times this number. It's a rectangular cross-section. If you use a round bar, then of course you'd use the area of a circular cross-section. Now I don't want that to change as I copy this formula down, so I'm going to do that. And look at that. Only 129 pounds, but we end up with 6.5 KSI of stress in our material. And if you've done calculations with KSI, that is not insignificant. That's a fair amount of stress. So I'm going to copy that, and then the same thing, I'm going to go down here, I'm going to press shift to get to the end of my column, and then I'm going to paste that formula in, and now I have all my stress values. Okay. So let's put in a graph. Let me drag this down just a little bit, make a little bit of room. So I'm going to go in here to insert Now let me highlight my columns first. So I'm going to click that. I'm going to hit my shift button again. I'm going to go down here. Now I have these two things highlighted. And if you're making a graph in Excel, it's always easiest if you put the X values on the left and the Y values on the right, the ordinate and the abscissa, in that manner. Now if I go to my scatter plot, I'm just going to do data points, and I'm going to do that. Let me move this up to the top panel. Now the default plot settings on Excel are pretty horrendous, but this gives us an overall view of our data. Now one thing that you notice, you see all of this kind of garbage right here. So what happens when you do a tension test is you're going along and you're measuring what's going on with your material, and it comes down and you decide I better take that extensometer off before the specimen breaks. Extensometers are fairly expensive. They're usually $4,000 or $5,000, and if you leave one on while the specimen breaks, you could damage the extensometer. So you try to get that off before that sudden pop at the end of our tensile test. And when you take the extensometer off, that means that you're no longer collecting any strain, but as you take it off, you get all these garbage reading values right here. These things are not part of the measurement. They're just spurious junk in the data. So we need to get rid of that. Let's see if we can figure out where that happened. Let's go down to the end of our data file. Now remember, the left is the strain and the right is the stress. So even though the stress values continue to be collected, and they're good numbers, the strain values have gotten to be where they're garbage. And I'm looking at this, and look, we got 0.146 strain, 0.154, and then here it is. It starts to decrease at this point. So at this point is where I think we have no more good data to be collected from our extensometer. Now we have to be a little bit careful here. We want to make sure that we have captured the peak of our stress strain curve. And looking at that, looks like we're around 180. So I can safely get rid of all of this data from here down to the end of this plot. And that'll clean that up a little bit. Looks like we still have a data point over here that looks kind of weird. I'm going to hit end and up. Oops, end and up. And this value seems to have jumped too far too quickly in the strain axis, so I'm going to get rid of that one as well. Alright, so now our stress strain curve looks fairly reasonable, with the understanding that this will continue to fall and then eventually break somewhere out here, but we just don't have the data for that. In an engineering stress strain curve, we're typically most interested in the ultimate stress and the yield stress and the modulus of elasticity. So we have to make a note. We need to understand that we did not capture the failure engineering strain in this plot. Alright, so now we've cleaned that data up a little bit, and I'm going to get rid of this bar and just take a look at this top. Now it's probably a pretty good idea to go ahead and save our spreadsheet here, and I'll just call it book 1. Now if we look at this chart, it looks like we have a very nice linear segment to our stress strain curve. This was a steel material. It's a fairly high strength material, so that does look pretty good. Let me copy this chart so we have a backup of it. And I'll just paste it right here. And let's change the x-axis values. And we'll zoom in on the initial portion of the stress strain curve. So this is strain in inches per inch or millimeters per millimeter. Let's make the maximum something like 0.02, 0.05. We'll go to that first data tick that I have there. And we can see here, just like we talked about initially on the page that I had, we have stress, but we have no strain that's been recorded for that. Now, what I'm gonna do is I'm going to overlay another chart on this particular plot, where I'm going to find the modulus of elasticity of this material. So I'm going to select data. I'm going to add a series. I'm going to call this maybe modulus. Modulus line. And I want the initial portion of the stress strain curve. So maybe that only goes out to, let's see, probably should be less than 0.005 on our strain. So I'm just going to select a bunch of data, and I don't want to go too far. Let's try up to here. Okay. And I'm going to copy. I'm going to say OK. I need to get that into that one. If I can find the right value. Yeah, for some reason this is acting a little goofy. Let me fix this here. Okay, so I just pasted it in, but now I want to change this to be the strain column, so I'm going to put a G right here. Excuse me, change it to the stress column. So I'm going to put a G in these two spots for the Y values. Okay. And it looks like I've gotten maybe a little bit too high. So I'm going to take off maybe 20 data points or so. So I'm going to go in here and make this, how about 150? Let's see what that looks like. That looks like it's still pretty good on the straight line portion. There's a little subjectivity to this. Okay, so now I'm going to select this line. I'm going to add a trend line. Now I'm selecting the red line. I'm going to do a linear, and I'm going to display the equation and the R squared on the chart. Stick some over here. Let's move these so we can see them. Alright, and R squared is 0.996. That's really close to 1, so that is a pretty good fit to a line. And we're going to format the trend line label with the number. Okay, so I changed the digits displayed for the modulus, and looks like I got 28.6. Now that seems like it's a little bit low for a modulus of elasticity, so let me, for steel, let me get rid of a few more points. We may still be on a little bit of a curvy part onto this. So let's take maybe the first 100. For that red line. Okay. And that seems a little more reasonable. So I think we got a little bit into the curve here. So 30.5, that might even be a little bit too stiff, but you can see by changing the data range, you can alter your modulus of elasticity a little bit. For steel, we should expect about 30 million psi. And here we have 30.6. So I would say we're pretty good. Let's maybe take another 20. We still have an R squared of 1. Okay, so there's 29.9. So we still really have a pretty good straight line. It's just the data is being biased a little bit by some of this initial data. Okay. So when we do our modulus of elasticity determination, we do want to take the slope of the best fit line through the data of the linear portion. You do not want to do a best fit line of the entire blue curve, but only a portion of the data that reasonably is along a straight line. So this looks pretty reasonable here. Alright, now what we're going to do is we're going to use this information to help us figure out how to draw in a correction for the stress strain curve. Let's go back to our page. Now we're only going to be looking at the initial portion of the stress strain curve. This part right here. And that part is an equation of a straight line. It's like y is equal to mx plus b. But we're using stress and strain, so it's like sigma is equal to the modulus of elasticity times epsilon plus some sort of offset. Now this offset is determined by the value where the x is equal to 0. What is the y value when x is equal to 0? So this distance is the offset in this direction. But really what we want is the offset in the horizontal direction. We want to know what epsilon is when y is equal to 0, or when sigma is equal to 0. Let's do it in terms of y's and x's. So when y is equal to 0, we have 0 is equal to mx plus b. So the x value should be equal to minus b over m. Let's go back to my spreadsheet. We'll calculate a shift value, and x is equal to minus b over m. So let's put in b. I'm just going to type it in. There is a way to make it automatically show up in a spreadsheet if you're doing lots of stress strain curves. And here's my slope, 29,912,442. We're going to go ahead and throw all those digits in there for these calculations, but in the end we'll only keep 3 significant digits. All right. And then the shift value is going to be minus b over m. Right. So that doesn't seem like a small value, but it will be just enough to move everything in that whole stress strain curve a little bit over to the right. So now what I'm going to do is I'm going to make a new column. With my shifted strain. Go down one more. There we go. Which is going to be this strain value. And now I'm going to have to add. Well, it's got a negative in it. So what I'm going to do is I'm going to subtract this value, which will effectively increase the strains everywhere. I'm going to use that $ trick. I'll find the end of my data. Go up there and I'm going to paste those formulas in. Now this is still inches per inch. This will be stress, and this will be in PSI, pounds per square inch. And now I'm going to just use the same values everywhere. There's no shift in the stress column. Let's go back to this picture, copy it, and paste it over here. Scoot this over a little bit. Now I want to use columns T and U, so I'm just going to edit the data for series 1, and I'll put T and U in here. Now it's important that you do not use the arrow keys while you're in these series X and series Y values. That'll mess up everything. So use the delete button and use your mouse to get to the right spot. Yeah. So now our stress strain curve starts and ends at 0. If we want, we can do another fit line, and then we can see that the intercept should be 0. Well, let's go ahead and do that. Let's see where we were at here. We went to 120. Let's go to this graph right here, and then to add a series. We want to go to about 120. And then I'm going to paste this in here. I'm going to change this to U. Okay. And then select that by left clicking, then right click to add a trend line. I'm going to do a linear. I'm going to display the equation and the R squared on the chart. And so now our intercept is pretty much 0. This number is insignificant compared to 8,000 something that we had before. So we have 0 stress and 0 strain for this graph. Alright, now we need to do a couple more things before we clean this up. Let's go ahead and find our 0.2% offset yield stress. I'm going to take it, I'm going to copy this graph and paste it in here. Now, if you wanted to, and it might be faster, you can just print this plot out and then use a ruler to find your 0.2% offset yield stress. Let me show you how you can do this with Excel. So we know that, let's go back to our page here. So some materials use the 0.2% offset method to find our yield stress value. These are typically materials that look very similar to this, where it's very curvy right here, and there's no well-defined yielding point. The idea with the 0.2% offset yield stress is that we go along here to 0.2%, which is 0.002 on the strain axis. Inches per inch or millimeter per millimeter. And then we have a line that we draw in that is parallel to the initial portion of the stress strain curve. And the intersection point of the stress strain curve with this line is the 0.2% offset yield stress. So this line has the same slope, but it has a different intercept value. So we have y is equal to mx plus b, and we have the case when y is equal to 0, our x value is equal to 0.002. Okay, so if y is equal to 0, we have our modulus of elasticity times 0.002 plus the intercept. Now this we found from the previous step, so we can find that our intercept value for this line is going to be minus e times 0.002. Now we need one more point on this curve to define a line. Let's go back and look at our stress strain curve here. If I look at this, it looks like if I use 180, well, let's just go ahead and use 200 KSI, 200,000 PSI for my maximum stress. So now, if y is equal to 200,000, and we know b, then we can find x. So 200,000 is equal to modulus of elasticity times x plus my intercept, which I have already found. So the corresponding strain value for 200,000 psi for this curve, this just straight line curve, is going to be 200,000 minus b divided by e. Right, so we're going to use that information in our spreadsheet. Let me bring that over here so I can see it on my other screen. And this would be our 0.2% offset line. Right. Now we need our slope. This is our modulus of elasticity. And it's the same slope that we had over here. So that was 29,912,442. We have a y value of 0 and an x value of 0.002 inches per inch. We can calculate our intercept, and from that equation that I just showed, it's going to be equal to minus e times this x value. All right. Now that we have that, then we're going to find a second point. We're going to take a y value of, let's do it this way. Put it right under here. 200,000. And we're going to have an x value that's going to be equal to this value minus the intercept all over our modulus of elasticity, which is in this cell right here. All right. So now what we're going to do is we're going to add another series to this chart, and this will be the offset line. I'm going to use the x values here, and the y values are going to be AF. I kind of put those in a funny order, but this will still work. All right, now let's something looks funny. Let me see what I did here. I got way too much strain, so let me just check everything. And here's the issue. I see that I didn't divide by my modulus term right here, so I'm going to take care of that. Okay, so that looks a lot better. Now, on this graph, you see I have these two data points. What I really need is a line. So let's do a solid line. And let's make that maybe a black color. Okay. Now, in order to determine the 0.2% offset yield stress, I need to figure out where this intersection point is. I need to rescale this axis on this graph. So maybe if I go to 0.01, that looks pretty steep. Let's change it just to make it look a little bit better. Go to 0.02. All right. And I'm just going to hover over here. So I'm looking at this data, and to me it looks like it's 150.5 psi. KSI rather, 150.5 KSI. Alright, I'm going to save this again. Now, here's the important part. Now that we've figured this stuff out, we really need to make a much better plot than what Excel gives us as the default. So let's start with changing our strain and our stress into more appropriate units. The standard way to designate strain is in percent. So I'm going to take this value in inches per inch, and I'm going to multiply it by 100. Find the end of my data. I'm going to copy and paste this down here. And my stress, I'm going to put in KSI. If you're working in SI units, you probably want this in megapascals. So I'm going to take this value and I'm going to divide it by 1,000 to get into KSI units. I'm going to paste that in there like that. I'm going to make a new chart. Let's start with this one. Let's see. Let's just start over the brand new chart. I'm going to highlight the X and the Y column, and shift and down, and then I'll insert. I'm going to do a scatter. And there's my data. I'm going to get up to the top. I'm going to cut this. I'm going to paste this up in here so I'm on the same level. Alright, so this looks like garbage in my opinion. So let's fix it. Get rid of that. I like the ticks on the inside. We'll try to find the chart. There it is. We're going to format the axis. Goes out to 16%. That's fine. Let's go tick marks on the inside. we have these nice values here for these minor these grid lines. But let's put some grid lines on the vertical axis. Okay. The golden ratio is 4:3. That's why we have 4:3 format monitors. So it's a good idea to try to scale your plot to a 4:3. Let's fix this one. I'm going to have the ticks on the inside. Okay, I'm going to go up to my chart tools, format, and we need an axis label. Let's see if we can find that. Okay, chart titles, axis title, horizontal axis title, title below the axis. That's fine. Brings it down there. Select that. Now this is going to be strain. This is E. I'm going to use E for strain for right now. And we should first use strain, comma, symbol, and then the units in parentheses. Now we have percentage strain. I'm going to highlight that symbol. I'm going to change the font to symbol, and that's going to turn that into the epsilon. Let's do a rotated title on the vertical axis. In the same way, we're going to go stress, comma, symbol. I know S will turn into a sigma, and then the units on this chart are KSI. Change the font. Alright, so that's starting to look a little bit better. We should add a text box in here. Title of the test, name of the operator, the date. Put in some other relevant information. Our modulus of elasticity. Let's go and find that value. We said it was 29.9 times 10 to the 3 KSI. Oops, I hit the wrong button there. I want to change that to a superscript. Offset yield stress, I'm going to change it to symbol, sigma sub y, 0.2%. We determined was 150.5 KSI. If we look at our data, think we were around 180 for the ultimate. We can find that too. Let's just page down through our data. Maybe we didn't quite get to 180. Looks like 178. KSI. Alright, so we're going to change this to a Greek font symbol. Change that. We're going to make these subscripts. Okay. Now I see it kind of goes through our, see our grid through that. So we're going to go in here and we're going to edit the fill. No, it's no fill. Let's do a solid white fill. And should be an option for a border. Okay. And maybe just to make this look a little nicer, why don't we do something like that. And there we have it, a nice looking plot that we can print out or put in a publication for showing the stress strain curve of our steel. So it does take a little bit of work, but you can make this look pretty good in Excel. The only other thing I might do is I might take this and move it down in size a little bit so we can see that a little nicer. Okay. Alright, so there we have it, a stress strain curve with our 0.2% offset determined by rescaling our axes and doing all this in Excel. And we found out how and why to correct our stress strain curve for an initial preload.